In the last video we looked at the idea of torque, and now we're going to look a little more closely at some of the more complicated mathematical ways of expressing torque. To start out with, we're going to talk about the vector cross product. So there are two main ways of multiplying vectors. We have the dot product, which we've seen a bit with work, was force dotted with the distance. But now we're going to look at the vector cross product. It's defined like this. It's the determinant of this matrix here, which is made up of the components of the vectors a and b, and then you also have the unit vectors I, j, and k that give directionality. Now if you remember with the vector dot product, it's sometimes called the scalar product because you get a scalar out. Here we don't. We get a vector out of multiplying these two vectors. And here's this nice long ugly formula. You might want to jot that down because you'll have to use it occasionally. If you know how determinants work for 3x3 matrices, then you can just figure it out from this matrix here, but it's probably quicker to just write that down there. Alright, now if we're just interested in the magnitude of this vector, that is the result of the cross product of two other vectors, then we just have the magnitudes of the original vectors times the sine of the angle between the two of them. So a lot of times this is all we're going to have to deal with, and it will be nice, but occasionally we'll have to use that big ugly formula on the previous slide. To find the direction of this vector, we're going to use what's known as a right-hand rule. We're going to end up with a bunch of those in electricity and magnetism. But the idea is that you point your fingers in the direction of vector A, and then you curl your fingers towards vector B, and that forces your thumb to point in the direction of the product, the cross product of those two. So that's how you get your directionality. So the product of two vectors, the cross product, is always going to be perpendicular to vectors A and B. So if B were over here, you'd point your fingers at A, but you'd have to turn your hand upside down to curl your fingers toward vector B, and in that case your thumb would be pointing down instead of up, and you would get the opposite direction for the vector cross product. Now in the previous video, if you remember, we looked at forces acting on a door, and this was the hinge over here. So if I'm exerting some force off in this direction, say, and that would be the direction of my force, and then the lever arm would be from the axis of rotation here to the point where the force is applied, so that would be my r vector. And I told you that we wanted to take the torque was the perpendicular component of either r or f. We'll take f in this case, so r times the perpendicular component of f. Well, the perpendicular component is going to be sine, right, because we want this component here. This is f perpendicular. It's going to be sine of the angle between the directions of these two vectors. So that tells us that this vector cross product, or at least gives us a hint anyway, is a valid way to describe torque. And in fact, that's exactly kind of a more robust definition of torque, is the lever arm vector crossed with the force vector. So in this case here, you've got r cross f. The torque vector would point into the screen here due to the right-hand rule. Oh, sorry, I lied. Out of the screen. Point your fingers in the direction of r, curl them in the direction of f. So r is pointing this way, right? So this would point out of the screen. Okay. Here's a little example of actually using that big ugly formula. If we have r defined in the xz plane, just to make it confusing. So r is going out this way, and then we have f, which acts only in the x direction. So if you do your right hand rule, you'll do r cross f, and your thumb will be pointing up. So the torque vector would be pointing in the positive y direction here. But if we want to actually find the vector notation of this, we're going to start with that big ugly equation here. Now r always has to be your first vector, so these components are essentially the components of A. So let's go ahead and write those. We've got an I, no j, and we have a k. So we have an AX and we have an AZ, and those are both equal to 1.2 meters. And then for our b vector, we just have an x component. So bx is equal to 150. Everything else is 0, so we can get rid of most of all of this. Okay, so this guy goes away to 0. That guy goes to 0. This one stays. That one is 0. That one is 0. And that one is 0. So we're only left with one thing to calculate. So not too bad. We take the z component of the a vector, which is 1.2, times the x component of the b vector, which is 150, and that is going to be in the j hat direction. And then we just multiply, don't forget our units, so meter newtons, because we're talking about torque. And this is our torque vector, and it is in the I hat direction. So typically, when we do have to deal with this, a lot of them will cancel out. Sometimes you might be left with 2 or 3, but rarely will you have, all 6 components that you're dealing with here. All right, that's all.